nice little system to study in the lab, especially as it relates to frequency response, and more specifically, linear system dynamics is a little electromechanical voltmeter. I like this system because it has, it has a lot of the elements of what is sometimes introduced in dynamic systems and controls. It's got electrical, electromechanical, and it's got some rotational dynamics, and it's sometimes kind of hard to build a system that is going to exhibit linear behavior, and this is a good one. And then specifically, we like to study the frequency response, and sometimes we've also studied this in a controls context, trying to control the position of this needle here. It's nice because it has has plus and minus input. It's a DC. It's low current, so it's easy to drive. The device is, this. I've got a link on the slides here to the actual SparkFun meter that we're currently using in the lab, and we've kind of made some changes to it because we're also using it for some vision experiments. I'll talk about in a related video on experimental measurement of frequency response. The device is based on the classical kind of galvanometer movement or D'Arsonval movement, where you basically pump some current into the coil here, right? And that coil current interacts with a magnetic field here shown, created by some permanent magnets. In this actual rendering, and actually there's also a spring in some of these devices, so you put in some current, a DC current, and it'll move. It'll also be restrained by that spring, so it doesn't just keep flying around like a motor, right? So it as soon as you bring the current down, it goes back to its unrestrained position and so on. So that's how these meters work, right? You can then use them to measure current, or if you calibrate it to a certain position, volts on this scale. And very classic device. Okay. Also classical electromechanical interaction that you learn about from starting high school physics and so on. So the actual device that goes into these meters, though, is a little bit different. I broke one down so you can see this is not specifically this meter, is another one that we used to use, but just so that you can see some of what's done in the design of these is the you might be able to see it better here, but you see how that the axis here, the coil, the rotating or moving coil, as it's engaged, it moves, and it actually stays, in within the magnetic field as shown here, so that the field is always radial, and so you don't have this angular dependence that you see in this case, right? And so that makes a big difference, because then that torque that's induced is related, and this is important when you're thinking about building a model. The torque that's electromechanical in nature is going to be related to the current, right, through the meter, and there's going to be a constant here that is going to depend on a lot of things. Like it depends on the B and the magnetic field density, and also maybe the number of turns, and it could depend on position. So if you take out that factor on position, then this is a constant, and we're going to call that little r sub m. And it's like, and if you think in context of bond graph modeling, I'll show you in a second that an effort in rotation related to a flow in current, and that transduction is sorry, this is current, say in this direction, torque. Sorry, I messed up there. So that effort and flow, then, if you put it in a bond graph, right, and we use a gyrator because the torque induced is related to the current. It crosses right into effort flow, and we use a little constant there. If this was a function of theta, we'd put a little function of theta there, but it's not in this case because of the design. And then, of course, you also have this, we call something that's called back EMF for motors, right? But that back voltage, this is a meter current, and then over here we have angular velocity, So we'll use this little gyrator in building a model. Okay. And so here I'm showing a schematic now of that system. Note that sometimes these meters have an external resistor and it controls the current so that you can control how much angular deflection you get. They respond to really small currents, so sometimes you put a limiting current limiting resistor in there in series with the internal resistance of the coil. So the total resistance is whatever you have on the outside, the series resistor plus what's the inside. Sometimes we'll remove that, measure that coil resistance, or measure the total. There's also some inductance. Sometimes it's a really small inductance. So in the model, you can see here, I'm ignoring it. This is a bond graph here. So I've got a series resistor. Here's the gyrator that's putting me into the rotational domain. There is some inertia. There's the compliance, the K sub M, J sub M, and B sub M. There's a little bit of linear friction. The device is really nice. Unlike the DC motors that we study that are brushed commutated motors. They have a lot of stiction and friction in there. This is a really nice linear friction in this device. That's why I said you get a really nice linear type model that is very much like what you might study in textbook problems. So here's your bond graph. I've applied causality. And I'll show you the state equations on the next slide. So the two states, you could either choose the momentum. I like to choose omega instead. H and omega are related through the moment of inertia, so you can use either one. We have a better feel for omega, so sometimes I switch it, but strictly speaking, we write a momentum equation, and that's here, and that's the sum of the torques, and you can follow this on your own by looking at the slides again. At the end of the day, you get a couple state equations, and I'm writing it in terms of omega and theta. I'm also putting an output equation there just so that I can use a formulaic approach to getting the transfer function. But getting the transfer function, you can do that a lot of different ways. You could go straight from these equations, do the Laplace transform, or you can use a state space conversion into the output over the input into a system, and for a single input, single output system, get a really nice formula in terms of little matrices, and do this all symbolically if you like by hand. For 2x2 is not too bad, but a lot of times you can put this into a symbolic processor in Python or MATLAB, and you get a transfer function at the end of the day that looks like this here. Oops. Right here, right? And this is nice because it's a standard second order system, as we might expect. This right here is your omega n squared, right? This, strictly speaking, this term in front of the s, right, is like 2 zeta omega n, right? So you can see we don't know a lot of these parameters, right? We'd have to measure the r sub m, which would be tricky. The j is really small. We've done it before. It turns out we need to introduce dynamic experience to do that and measure current and so on. We're going to avoid that in the frequency response lab, and we're strictly going to focus on getting the amplitude and phase functions, and we'll talk about that shortly. So sometimes we put this into another standard form that looks like this, where we divide by omega n squared, and this defines this k up here as a gain, and this is what we're going to call the DC gain, right? Why do we put it in this form? Note that we divide. This is a standard form. Note that it's very common to think about when remember S is equal to j omega, and as omega goes to 0, think about on a plot, like let's say you have a frequency response plot, and here you have your G. As omega going to 0, that frequency, we never quite get to 0, but 0 with frequency, but when frequency strictly is equal to 0, that's sometimes what we call DC. It's like constant. So if a voltage, we say it's a DC voltage, it's a 0 frequency voltage. So the gain, the DC gain, is the ratio, the magnitude ratio G at omega equal to 0. Look at this equation as omega goes to 0, right? K, the gain, and I'll talk about this on a separate slide, when omega equal to 0 is just K, right? And that's easy to measure, and we'll do that in the lab. Okay, so that's why we put it into this nice form. And actually, if you learned how to sketch Bode plots, which you can do as well, breaking it up into this form, you first think about it this way. The standard second order system looks, starts at 0 dB and it goes to here, and at omega n you might look something like this. The gain basically is a constant. So this is the standard second, which is just the bottom part. You add a k, you add those together. So basically, if you know what I'm talking about with sketching, then basically you can see that k just bumps it up or brings it down, and so it basically the final transfer function, frequency response will look like that. Okay? And if you're not familiar with how to sketch Bode plots, don't worry about it. A lot of times nowadays we all throw it into a program, and use Bode, or we plot them as I've shown in the related video. So now I'm going to take that transfer function and get the frequency response function by making s equal to j omega, and now I get this complex function, right? And note how I have the DC gain here on top, and this is your standard second order form, putting j s equal to j omega, right? And now I can get my magnitude function and my phase function, and these are textbook second order magnitude and phase, with the exception of you have that extra gain that is the DC gain, right? And remember that you're going to measure that explicitly by putting actually constant voltages in there. And remember, in the context of a voltmeter, G, the ratio here is basically theta over the input voltage. So if you put a constant voltage, it gives you a constant theta, and so you can measure that by just putting put 1 volt in, measure theta, and we'll do that, and then we'll measure it with different sinusoidal inputs, and I'll talk more about that again in a related video on experimental measurement. Lastly, just to wrap up with that DC gain discussion, which I already talked about, when I make S or omega go to 0, you can see for the analog meter how your DC gain is equal to K. This illustrates nicely sort of frequency response in this really quick video. So what I'm doing here is varying, keeping the voltage amplitude constant, but with a function generator, just varying the frequency from low frequency to high frequency. So you can see how it sort of passes high frequency, you're going to see the amplitude drop off. It follows the second order system very nicely, and this is kind of what we expect to see in the lab. So let's just kind of quickly take a look at that. You see low frequency, and I'm starting to increase the frequency. Then you can see now it's beyond a sort of it's rolling off, and you're hardly getting. And now I'm going back. It's passed to the resonant pretty quickly. So you can see how it follows that curve of what you expect to see. Sort of it's flat for a little while, resonates, and then it drops. Okay, so the behavior follows kind of nicely, at least qualitatively, what we expect to see in the lab and what we've seen from the model. And you'll measure that when you go to lab. In a related video, I'll talk more about experimental measurement of frequency response functions. I will discuss now in 2 related videos how to get these frequency response functions from a theoretical model. Then now we'll talk a little bit about how do we measure them in the lab.